What if the night sky you think you know is already out of date? And what if, while most people were sleeping, a machine in the Chilean mountains quietly caught the universe changing in real time? Before we go deeper, do me one favor. Tap like if you love mind-bending space stories, subscribe if you want truth over hype. And share this with one person who still thinks astronomy is slow and boring. A few minutes ago, the internet started doing what it always does when something huge happens in space. Headlines exploded. Clips spread fast. People rushed to say the Vera Rubin Observatory had just changed everything. And for once, that dramatic reaction was not completely wrong. Because this is not just another telescope taking another pretty picture. This is a machine built to watch motion, change, danger, mystery, and surprise at a scale human beings have never had before. It does not stare at one tiny patch of space for hours and call it a day. It sweeps, it returns, it compares, it notices when something has moved, brightened, dimmed, exploded, or appeared where nothing was seen before. In other words, it does something that sounds simple until you realize how hard it is. It watches the sky like the sky is alive, and in a very real sense, it is. Stars pulse, galaxies collide, asteroids drift, black holes flare, supernovae ignite and fade, distant icy worlds crawl through darkness. And for most of human history, we missed almost all of that motion because our tools were too slow, too narrow, or too limited. We were getting portraits of the universe when what we really needed was a live feed. That is why the Vera Rubin Observatory matters. It sits on Cerro Pachon in Chile, high in the Andes, where the air is thin, the skies are dark. The conditions are among the best on Earth for looking into deep space. That location was not chosen because it sounds dramatic in a documentary voice. It was chosen because every bit of moisture, every bit of turbulence, and every bit of stray light can steal clarity from the sky. If you want to build the most ambitious sky survey in history, you do not compromise on the view. And the machine placed on that mountain is absurd in the best possible way. Its main mirror is 8.4 meters across. Its camera is the largest digital camera ever built for astronomy, about 3,200 megapixels. That number is so huge it almost stops meaning anything. So think of it like this. One image from the system contains so much detail that displaying it at full resolution would require a giant wall of ultra-high definition screens. Not one screen, not 10, a wall. But even that is not the most important part. The most important part is speed plus repetition. Rubin is built to image the sky again and again and again. It takes a view, moves, takes another, keeps going through the night, then comes back to the same regions later and checks what changed. Over time, those images become more than isolated snapshots. They become evidence. They become history. They become a time machine made out of data. That is the heart of its 10-year mission, the Legacy Survey of Space and Time, often shortened to LSST. And that name tells you exactly what makes this observatory different. Most telescopes give us pieces of space. Rubin is designed to give us space across time, not just what is out there, what is happening out there. That difference changes everything. Because the universe is not a museum full of still objects sitting politely under cosmic lighting. It is an active place full of events. Some are slow enough to unfold over millions of years. Others burst into existence in hours or minutes. If you're not watching often enough, you miss them. If you're not watching wide enough, you never knew they happened. And this is where the story becomes bigger than a cool new observatory. Rubin is named after Vera Rubin, the astronomer whose work helped reveal one of the deepest mysteries in all of science. She studied how galaxies rotate. Based on the visible matter inside them, those galaxies should have behaved one way. But the data said something else. The outer regions were moving too fast. There had to be extra gravity coming from something unseen. That invisible something became one of the strongest cases for what we now call dark matter. Think about how wild that is. A scientist looked at the motion of stars and realized the universe was hiding most of its mass. Not because she guessed, not because it sounded exciting, because the numbers refused to fit the obvious story. That same spirit lives inside this observatory. Watch carefully, measure honestly, trust the evidence, even when the answer feels strange. And the reason people are so shaken by Rubin's early results is that this machine is already proving it can do far more than make beautiful images. It is showing that our entire relationship with the sky is about to change from occasional discovery to constant discovery. That is not a small difference. It is the difference between checking a forest once a week and having sensors on every tree. It is the difference between hearing about earthquakes days later and feeling the ground move as it happens. Rubin is turning astronomy from something that often looked backward in large chunks into something that can react in near real time. So what actually broke the internet? It was not just one image. It was what the image represented. During its public first look, Rubin released early observations that immediately showed what this machine can do. One of the most talked about views combined observations of the Trifid Nebula and the Lagoon Nebula. glowing clouds of gas and dust where stars are born. People online focused on the beauty first, and fair enough, because the image was stunning. But scientists saw something deeper. The image was built from hundreds of exposures gathered over hours, stacked into a view packed with extreme detail. That meant Rubin was not merely capturing bright objects. It was pulling faint structure, hidden stars, and delicate features out of darkness, with a speed and scale that signaled a new era. Then there was a view of the Virgo cluster region, loaded with galaxies scattered across the background, each one a city of stars. Again, the casual viewer saw beauty. The astronomer saw a warning shot. If these were just early looks, what happens when the system runs at full strength for years? The answer is almost hard to say out loud without sounding fake. Billions of galaxies cataloged, millions of alerts, an avalanche of moving objects, a flood of transient events, a living map of the southern sky, updated again and again. And here's the part that makes this story feel unreal. Even before the full long-term survey settled into its rhythm, Rubin's early observations were already uncovering huge numbers of previously unknown objects in our own solar system. Thousands of new asteroids appeared in a shockingly short time. Near Earth, objects were identified and tracked. Distant trans-Neptunian objects far beyond Neptune emerged from the dark edges of the solar system. Already known, asteroids had their orbits refined with better precision. That matters for two reasons. First, planetary defense. The more accurately we know where rocky objects are and where they're going, the safer we are. Second, solar system history. Every asteroid, comet, and distant icy body is like a leftover clue from the formation of the planets. These are not just random rocks. They are fossils of a violent beginning. And Rubin is about to find them in ridiculous numbers. If you are still with me, here is your mission. Hit subscribe before the next discovery hits. Leave a comment with the one space mystery you most want solved, and send this video to a friend who loves saying nothing ever happens anymore. The sky would like a word. Now let's slow down and understand why astronomers are acting like they have been handed a superpower. For decades, astronomy has had an ugly trade-off. You could go deep or you could go wide. You could study a tiny patch of sky in incredible detail, or you could cover a huge area with less detail and less frequency. Doing all three at once, wide, deep, and fast, was brutally difficult. Rubin attacks that trade-off directly. It is wide enough to scan huge sections of the sky, sensitive enough to detect faint objects, fast enough to revisit the same regions over and over. That combination means it can find things that are rare, fleeting, hidden, or moving. Imagine trying to understand a city at night by opening a window for 1 second every week. You might learn where the tallest buildings are, you might spot a few bright signs, but you would miss traffic patterns, police sirens, flickering apartment lights, storms rolling in, streets going dark, and crowds gathering. Now imagine instead you have a time-lapse view of the whole city, night after night, with enough resolution to notice tiny changes. Suddenly, you are not guessing, you are tracking life. That is what Rubin is doing to the sky, and the deeper implication is enormous. The future of astronomy will not belong only to the people who build telescopes, it will also belong to the people who can handle data. Rubin is expected to generate an ocean of information over its lifetime. Night after night, the observatory can produce alerts when it detects something new or changed. An asteroid shifted, a star brightened, a likely supernova appeared, a black hole feeding in a distant galaxy flared, a variable star dipped again, something moved, something exploded, something changed. That alert stream is one of Rubin's greatest powers, because some cosmic events do not wait for human convenience. A supernova can brighten fast and fade. A rare flare can come and go. A near-Earth object may need quick follow-up. If Rubin detects the event early and sends the alert fast, observatories around the world can swing into action. One telescope sees the change. Others investigate from different angles and wavelengths. Visible light, radio, infrared, X-ray. Suddenly, the whole planet becomes a coordinated observing machine. This is one reason the observatory feels like such a leap. It is not just collecting data for later papers. It is acting like an early warning system for the dynamic universe. And if that sounds dramatic, good, because it is. We are used to hearing about giant discoveries years after the fact, polished and packaged. Rubin shortens the emotional distance between event and awareness. Something happens in the sky, and the world of astronomy can know fast enough to respond while it is still unfolding. That has never been normal. And then there's the dark matter and dark energy question. Most of the universe is not made of the familiar stuff we can see. Ordinary matter, stars, planets, gas, dust, you, me, every building, every ocean, every animal, all of that is only a small fraction. Dark matter appears to shape galaxies with its gravity. Dark energy appears tied to the accelerating expansion of the universe. These are not tiny gaps in our understanding. These are giant missing pieces. Rubin cannot wave a wand and make those mysteries disappear overnight, but it can do something just as important. They can collect the kind of precise, repeated, large-scale observations scientists need to test models harder than ever before, by mapping how galaxies are distributed, by tracking how structures evolve, by measuring subtle distortions and patterns across enormous samples. Rubin helps scientists ask better questions with better evidence. Maybe dark matter behaves exactly as expected. Maybe it surprises us. Maybe dark energy remains stubbornly mysterious. Maybe patterns emerge that push theory in a new direction. But whatever happens, the argument gets sharper. And that is what real progress looks like. Not magic certainty. Better evidence that squeezes weaker explanations until something breaks. There's another emotional layer to all this that most viral posts skip over. Rubin is the result of patience on a scale the internet barely understands. This project did not appear because someone had a cool idea last month. It took decades of planning. The camera alone was a monster of complexity. Precision optics, massive data systems, calibration challenges, mechanical stability, software pipelines, operational reviews, teams spread across institutions and countries, years of work before the public got its first dramatic glimpse. That matters because it reminds us what discovery really costs. Not just money, time, discipline, repeated failure, quiet problem solving. People giving huge parts of their careers to a machine that might only fully prove itself long after the headlines move on. So when Rubin finally starts delivering, it is not just exciting, it is emotional. It is the moment years of invisible effort finally turns into visible truth. And already the results are hinting at something even bigger than the expected science goals. The history of astronomy is full of discoveries nobody set out to find. New planets, strange radio sources, unexpected cosmic explosions, weird objects with odd orbits, surprising behavior from stars. The universe has a habit of rewarding better tools with things we did not think to ask for. That may end up being Rubin's greatest gift, not just helping answer known mysteries, but revealing better mysteries. If the sky is being checked over and over with this level of depth and speed, then the chances of catching something truly unexpected rise. Maybe a rare kind of transient event, maybe a new class of moving object, maybe a pattern in outer solar system orbits that sharpens the Planet 9 debate, maybe something about galaxy evolution, maybe something no one has a neat label for yet. That possibility is why so many astronomers sound like children trying not to grin too early, because they know the machine is finally awake. And once a machine like this starts watching at scale, the universe stops being a collection of isolated wonders and starts becoming a stream of ongoing surprises. Quick pause. If you want more videos that cut through the hype and turn discoveries into stories, click like and join the channel. Share this with someone who loves asking impossible questions at 2 a.m. That kind of curiosity belongs here. Now, let's talk about the discovery machine side of Rubin, because this is where most people underestimate what is happening. When people hear telescope, they often imagine a scientist manually pointing at one object and taking a majestic photograph. Rubin is not that kind of instrument. It is closer to a survey engine. It is industrial-scale astronomy. It is systematic, relentless, and incredibly good at finding needles in a cosmic haystack. Suppose a faint asteroid moves slightly against the background stars. A human staring casually at two images might miss it. Rubin's system compares observations and flags motion. Suppose a star that looked ordinary yesterday suddenly brightens today. Rubin notices. Suppose something in a distant galaxy flickers in a way that suggests a feeding black hole or a supernova in progress. Rubin notices. Suppose a tiny frozen body far beyond Neptune shifts position just enough to reveal its orbit. Rubin notices. And every time Rubin notices, the scientific world gets an opportunity. That changes the economics of attention in astronomy. Before, rare events could easily die in silence because no one saw them in time. Now, they can trigger follow-up across the globe. It is as if the sky has gone from whispering into the void to sending notifications. There is something deeply human about that. We built a machine to help us not miss reality, because that is the uncomfortable truth. The universe has been putting on this performance forever. Explosions, collisions, flares, migrations, hidden worlds, invisible mass shaping motion. Most of it happened without witnesses, not because it was subtle, but because we were. Rubin narrows that gap, and the internet reaction is at least partly a recognition of that emotional fact. People can feel when a new instrument changes what is possible. They sense when humanity has built a new eye. The asteroid story alone proves the point. Early Rubin data quickly led to a surge in detections of previously unknown asteroids. That is not just a big number for a press release. It tells us the observatory is doing exactly what it was designed to do. It is efficient. It is sensitive. It is finding moving objects fast. Some of those objects are harmless and scientifically interesting. Some are relevant to long-term planetary defense. Some may help explain how the solar system evolved. And some may end up becoming important simply because their odd behavior leads to better questions. Then you get the trans-Neptunian objects, icy bodies in the outer reaches of the solar system where sunlight is weak. These objects matter because they preserve information from the solar system's early architecture. Their orbits can also hint at hidden influences. That is why every new distant object becomes another clue in a much larger puzzle. If enough of them show strange orbital patterns, arguments about unseen massive bodies in the far solar system become more testable. And yes, that is why Planet 9 keeps haunting conversations like this, not because astronomers are desperate for a dramatic headline, but because orbital patterns can point to something real. Rubin may or may not directly reveal a giant hidden planet, but even without a single clean image, it can still reshape the debate, by dramatically increasing the number of distant objects we know about and by tracking them better. That is what people often miss about discovery. Sometimes the breakthrough is not a cinematic reveal. Sometimes it is a pile of careful evidence that suddenly makes one explanation much harder to ignore. Rubin is built for that. And then there are supernovae, those astonishing stellar deaths that can briefly blaze with the brightness of whole galaxies. If you want to understand expansion, cosmic distances, and extreme physics, you care about supernovae. But timing matters. Catching them early matters. Watching how they brighten and fade matters. Older observing strategies often missed the opening act. Rubin's repeated scans give astronomers a better chance to catch these explosions close to the start, when information is still fresh. That means better data, better models, and more chances to connect an event with other telescopes before it fades. And remember, Rubin is not watching one little region. It is covering huge areas of sky repeatedly. That is the force multiplier. Wide, deep, fast. Those three words sound simple. Together, they are transformative. Now, let's talk about black holes for a second, because they are part of why Rubin's alert stream could feel so addictive. In distant galaxies, supermassive black holes can flare as they feed on surrounding material. Those changes in brightness can tell us something about how matter behaves in extreme environments. Rubin's repeated observations make it far easier to notice that variability across enormous populations of objects. That matters because modern astronomy is becoming more statistical. Scientists want to ask what the full population does. Rubin thrives in that world. It gives us not only dramatic stories, but sample size. And sample size is where weak ideas go to die. That same logic applies to galaxies. Rubin is expected to help catalog staggering numbers of them. Each galaxy has data about cosmic structure, history, motion, clustering, and evolution. Multiply that by enormous numbers and you get a far more powerful map of how the universe is built. That map matters for dark matter, dark energy, and understanding how the large-scale structure of the cosmos emerged. And because Rubin keeps revisiting the sky, it can connect structure with change. That is why astronomers are excited. For many of them, Rubin is not just a new instrument. It is the machine they have been waiting their entire careers to use. Some watched the concept grow for 20 years. Some built tools and software in the hope that one day the data would come. Some designed science programs around a future observatory that felt half mythical because it took so long to arrive. And now it is here, producing real alerts, real detections, real images, real science. You can hear the relief in that. You can hear the sense of arrival. And maybe the most exciting thing is this. We are still early. That is the part almost nobody really feels when a story like this goes viral. People treat it like the peak. But with Rubin, this is the opening scene. The observatory is entering a mission designed to last a decade. A decade of scanning, a decade of alerts, a decade of discoveries, a decade of refining our map of the universe. Imagine what that means in practice. Night after night. More moving objects, variable stars, and supernova candidates, more strange flares, better orbital precision, better population studies, better cosmology constraints, more chances to catch the unexpected, more opportunities for scientists across the world to work from the same giant stream of evidence. This is another huge point. Rubin is not valuable only for elite researchers. Large survey data becomes a platform. It gives students, teams, and institutions a shared foundation to ask different questions. One dataset supports many kinds of science. That means its impact spreads outward in ways that are hard to predict. The observatory creates conditions for discovery. That is a much bigger legacy. And if you think about it long enough, it becomes emotional in a different way. Human beings are tiny on cosmic scales. We live short lives on a small world around one ordinary star. And yet, we keep building better ways to ask better questions. That impulse is one of the most beautiful things our species does. Rubin is that impulse made physical. A mountain, a mirror, a camera, a decade of patience, and a promise to keep watching. If this story is lighting up your brain, help this channel reach more people. Tap like, subscribe, and share this with the smartest person you know. So what should we expect next? First, more of the obvious wins. More asteroid discoveries, better tracking, more transient alerts, more spectacular images that pull the public in and make people care. Do not underestimate that last part. Beauty matters. A breathtaking image can be the doorway to a much deeper understanding. Many people enter astronomy through awe. Second, stronger statistics. As Rubin keeps observing, scientists will move from exciting first examples to robust results. That is where theories start facing real pressure. One weird object can be dismissed, 10,000 similar ones cannot. Third, better timing on short-lived cosmic events. The faster you catch changes, the better other telescopes can respond. Fourth, sharper tests of big cosmological ideas. Dark matter and dark energy will be attacked by precision. Fifth, the wild card. The thing nobody can name yet. History suggests that when you improve power, reality surprises you. New windows create new questions. Maybe that future surprise is already sitting unnoticed in data that has barely been processed. Maybe it will show up as a statistical oddity. Maybe as an orbit that refuses to behave. Maybe as a new transient event. That is the real electricity around Rubin. It is not just that we expect answers. We see the shape of our ignorance. And once you see that shape, science moves. There is also something worth saying about the public side of this. A project like Rubin cuts through noise and shallow spectacle. It shows what human effort looks like when decisions point in the same direction. It shows that truth is still something we can work toward. Slowly, imperfectly, collectively, but genuinely, these stories matter beyond space fans. They remind us that reality is richer than the feed, that the universe is not running out of wonder, that careful people with hard tools can still reveal something real. And honestly, that might be why internet reactions become so intense. People are hungry for discoveries that are not fake. They want to feel that something bigger than the algorithm is happening. With Rubin, something bigger really is happening. A machine on a Chilean mountaintop is starting a 10-year watch. It will ask the same question. What changed? That question is more powerful than it looks. Hidden inside are questions about what moves in the dark and what explodes. What invisible mass bends the universe? What distant objects preserve the memory of the solar system's birth? What patterns appear when you start making a movie? What have we been missing because we were not looking often enough? That is why the phrase "broke the internet" actually undersells this story. The internet breaks every hour. Rubin is breaking our old limits. The people who understand that best are the scientists who now wake up each day ready. Imagine living in that state of readiness. Imagine seeing the stream of cosmic change finally start to flow. That is the emotional reality inside the astronomy community. Not just excitement, readiness, expectation, relief, the sense that a door is opened. Future generations may look back at this as the point when sky watching became tracking, the point when astronomy stopped collecting still frames and started building a living record. One instrument began turning the sky into an archive of motion, danger, beauty, and mystery. One more favor. Subscribe now and hit like so this reaches more curious minds. That matters more than you think. What if the night sky you think you know is already out of date? It is. Not because the stars suddenly changed tonight, but because our ability to notice change just leveled up. The Vera Rubin Observatory is not making the universe more active. It is making us less blind. The wonders were always there. The moving asteroids, the flickering black holes, the dying stars, the hidden structure, the clues pointing toward dark matter, the surprises nobody had language for yet. We were the slow part. Now we are getting faster. Now we have a system built to return, compare, detect, and alert. Now we have a machine designed not just to admire the cosmos, but to catch it in the act. This is about a new style of seeing, a new relationship between humanity and the sky. Less occasional awe, more continuous awareness, less wondering what we missed, more finding out. Every improvement in vision reveals how much more there is to learn. Rubin will help map billions of galaxies. It will teach us to think of the sky not as a fixed ceiling, but as an ongoing event, a process, a story still unfolding. Somewhere tonight, while people scroll past headlines, the observatory will keep watching. Another exposure, another comparison, another alert, another object moving against the stars, another ancient signal meeting a camera built by a species that refuses to stop asking questions. Small temporary creatures building instruments, patient enough to catch the universe revealing itself one change at a time. And if Rubin keeps delivering, this is not the last time it breaks the internet. It is the first time.